Okay, yeah. Then let's start with the talk. So the topic is high-speed data acquisition over HDMI. And if you have heard the FX2 ADC talk yesterday, I was looking at how can I capture data at high speeds and low cost. One thing that was really a limiting factor with those USB oscilloscopes is that they are only a USB 2.0 high speed. So you have 480 megabits and you get around 45 megabytes a second net rate on a typical PC. And what I also already mentioned, if you attach multiple devices to the same host controller on your PC, you don't even get the full bandwidth out of USB 2. So next obvious thing would be Ethernet. You also are limited to around 115 megabytes a second with 1 gigabit Ethernet. You also could do 2.5G Ethernet, of course, but if you want to connect an ADC, you want probably a small FPGA board, and there are not many FPGA boards that are cheap and have those connectivity options. 5 gigabits USB 3.0 is a huge step up in hardware complexity, and you need interface chips. For connecting the ADC, for example, I looked at small and cheap FPGA boards, and there's this Sipeed Tang nano boards which use a GoWin FPGA, and the small ones come in different sizes. So this is the amount of lookup tables. Up above is the smallest board has the most lookup tables. And they all have an HDMI port, but the I/O, if you want to use a parallel ADC and not JSD like we heard yesterday, you are then rather limited, because if you attach the ADC and some USB interface chip, Cypress FX3 or the FTDI ones, I think the Lime SDR uses the FTDI one. You need again many GPI or many pins, and with those small boards that simply doesn't work. One chip which is rather new is the WinChiphead CH569. It's also rather cheap, but unfortunately it uses some proprietary HSPI, that's what they call it, high-speed interface, which is also a parallel interface, either 8, 16 or 32 bits, and then you need some custom FPGA implementation. It has some CRC and so on, so you also cannot simply hook an ADC to it. The only chip where that works right now is the FX3, but I think it alone on DigiKey is like $33 a chip alone, so not really cheap, and you need many I/O pins. One interesting thing that probably is due to be released later this year, for one the FX4, which then also has some LVDS lanes, but there's a small lattice FPGA with integrated USB 3 PHY. And this is probably also interesting, but probably also not exactly cheap. So let me add one option to that list. So I looked at using those cheap Macrosilicon, or they think got renamed to Ultra Semi USB 3 HDMI grabbers. You can actually buy those for around $8 to $10 shipped with the case and everything, and it's basically a single chip solution which integrates the HDMI interface and the USB 3, and they come in different shapes, but doesn't really matter. Just one thing to keep in mind there was an older version which was USB 2 only, and they used the MS2109, and yeah, then I didn't actually try it. It might work as well, but then of course only with USB 2 data rates. So the ones you want to have are with U3 on there for USB 3, and they are also mostly advertised as MS2130 in the offering. So how does this chip actually look like? Yeah, rather simple. You have the video source transmitting and a HDMI 1.4 receiver inside the chip. There's a small MCU, 8051 of course, and yeah, then the video goes through this process chain here and ends up in the USB 3 device implementation and is being streamed to the host. Yeah, what we of course want to bypass somehow is this video process block up here, because yeah, I wanted to stream data through and don't have it changed somehow. At first I thought, yeah, it would be nice if I can do like 7 out of 8 bits or something like that with some lookup table, but as it turned out, this was not necessary. This chip can accept RGB input or YUV input and also supports HDR. It integrates the video scaling, so you basically select a resolution you want to capture, but it doesn't matter what you input. It is always rescaled or resized to this resolution. Same is true for the frame rate. We'll come to that later. But the output via USB is fixed to either raw 422 YUV, we'll come to what that actually is later, or MJPEG, which is compressed and not really interesting for our use case. The output, yeah, is a configured frame rate. So when you open the device, you say, I don't know, 60 FPS, and it will keep this clock no matter what is input. It will also do like a time rescaling of the input signal. This YUV or YCBCR is actually called chroma subsampling. So what they do is, if you use a regular RGB input from your laptop or whatever, the luminance, so the Y part, is not compressed. So you basically, for every pixel, get a luminance value, but the color, the chrominance, is in this case compressed. For 2 pixels next to each other, you only get 1 color value basically. And yeah, because the eye, the human eye is not so sensitive for color changes, it means it's used in all the analog TV standards and so on, basically a form of compression. And the output is YUV 422. Yeah, YUV and YCBCR are actually they are more or less the same thing, but not really. They use different lookup tables. So HDMI implements YCBCR. If you look at what HDMI actually is, you have like 3 high-speed LVDS channels that transfer the actual data, and they are 8B, 10B coded, just like JESD, like we heard yesterday. And in addition, you also have a clock channel, and it's pretty much the same idea like JESD or any other LVDS link. You also have the display data channel, which is just a fancy name for the I2C bus for reading the EDID EEPROM, or you can also transfer other things with HDMI, like remote control and so on. But you also have this consumer, I don't know, this is also a consumer equipment control line. But we actually do not care about those. This is also interesting. I think you have it in my block diagram later. If you want to do reverse control of the device, because it's more or less a unidirectional link, but you also can abuse this display data channel with this device to do some control of the data source. Typically, HDMI uses RGB, but there are modes defined where you can directly do YCBCR. And as I said, the output of the chip via USB is fixed to YCBCR. If you do not want any modification on the data, you better input also already that, so that there's less things that can interfere. Otherwise, you need to undo the lookup table somehow. And so I tried using that. And as you can see, because the data is already compressed by this chrominance subsampling, they basically have bits free. You can do 12-bit YCBCR. So the TMDS channel, so for RGB, the TMDS channels are like RGB and then every pixel each clock. But with YCBCR, they do 12-bit, and the upper bits are in channel 1 and 2, and the lower bits, which are unused and basically dropped by the MS2130 in TDMS channel 0. So basically that bandwidth of this channel is more or less wasted, but well. In order to tell the device that it is YCBCR input, I tried spoofing this via register writes and basically forcing it to that mode, but it seems like there's something still in there that requires the information from the HDMI side. And so if you know, DVI and HDMI are quite similar on the electrical layer, and the main difference is that HDMI adds so-called data islands for transferring audio. There are different data packets. In the data islands, you can transfer info frames, audio sample packets, and so on. There's also a guard band right before the active picture area starts. And then you have regular, so they are transmitted via the vertical blanking. And also the audio packets here via the horizontal blanking. And so although that device supports DVI input, if you want to use this YCBCR mode, you need to do proper HDMI input with those info frames, because there's one extended info frame where you can select or tell the device this is YCBCR, chroma subsampled input. And when I first was playing with this, I used the FPGA to generate one pixel, and it looked like that. And this is not exactly passing through the data unmodified. You see there's some sharpening going on. The neighboring pixels and even the pixels in the line below were being influenced by this one pixel that was set. Also, this is not really an accurate representation, because I just open it with VLC or whatever for this screenshot, and there, if you have YCBCR input, it will convert it back to RGB, so you can view it. So it actually looks a bit worse than this even. So this, after like a 1.5 week of fiddling around and flipping all kind of bits in this chip, I came up with this. And this is basically the magic that makes this work. So you have to disable sharpening, the luma processing. There's also some sub-pixel interpolation going on for the horizontal scaling. And so you have basically to do all this. And then it turned out you really get the data you put in out via USB untouched. And that's quite nice for this use case. Let's take a look at the block diagram, how this whole setup now works. So in the FPGA, you acquire some data. We'll look at some examples later, and put that into an async FIFO. This is so you can choose any clock you want that is not related to the HDMI clock, and also because there's still this vertical and horizontal blanking. We need to buffer the data for this time when there's no active video being basically transmitted via HDMI. The HDMI is supplied with a TMDS clock, which is, I think I have it on the slide later, the actual signaling used by HDMI. And the pixel clock is divided from that by 5, and this is then used to stream out the data. And every pixel clock I can transmit 16 bits. In the MS2130, you then have the HDMI receiver. It recovers the pixel clock from the clock line we've seen and aligns the channels. And if you underrun the frame rate you've set for the USB interface via this UVC or Video for Linux, it actually buffers this data, and in case there's an underrun, the last frame is simply outputted again. So this is quite nice, because if we add a frame counter, we can just throw away those doubled packets. And in general, the HDMI link is very forgiving for the MS2130. You basically can use any arbitrary pixel clock, and with this fixed frame rate and doubling, it doesn't really matter. So you can really do what the FPGA is capable of, and do not really need to worry about violating any timings, because it simply works. Also, what I mentioned, if you want to do some control of the acquisition device, like the FPGA, over this, there's an EDID emulation. So there's a RAM you actually can write via USB and use that. If you have a state machine that simply polls, like, I don't know, every millisecond or so, the EDID RAM, you can actually transmit commands this way into the FPGA to start sampling or set modes or whatever. So you can do this with an HDMI cable and do not need a second USB port. What is actually implemented now as a frame format basically is that the picture that is being output, at the start of the line, you enable the readout of the asynchronous FIFO, and either when the line is at its end, or when the FIFO is empty, the readout is disabled. And then same thing for the next line, and so on. And here at the end, the last 16-bit value is reserved, basically, where I transmit the payload length of the line, so you know how many of this data is actually used per line, as well as some status information, magic, frame counter, and you also can transmit a checksum. And this gray area, basically when the FIFO is empty for the line, is currently unused, and I simply transmit an idle counter, which I can basically use to verify whether the link is properly working. In order to reduce the amount of FIFO, which translates to the amount of block RAM in the FPGA, you need to buffer the data during this VSync and HSync. I tried playing with the actual timing, and the HDMI capture device doesn't actually care that much. You can reduce the VSync to 4 lines, and the HSync to 62 pixels. Remember, in the VSync there you also transmit these HDMI info frames. Luckily, they are right at the beginning, so you can really crop this quite a bit. This obviously increases the data rate you can transfer, as well as minimizes the amount of block RAM you require to buffer the data. So let's do a quick demo. What happens if you now open the capture device? How does this look like? So the gray area basically is the data that is being transmitted, which is then converted to RGB again. So yeah, it's not really, it's from an just noise from an HDD converter. And as I said, this at the end, you see this is the idle counter, which is just a 16-bit counter, which if there's no data to transmit, just send this counter value and increase it. That's why it's alternating in colors every time it wraps around. And you also
the shadow had a small icon or whatever in there.
Yeah, you could do that, right? And you also see, like at the beginning of the frame, there's no idle counter because the FIFO is full from the VSync. So it first needs to get rid of all the data it buffered, and then if you catch up, you have free cycles again. Right. So I played with a couple of boards just to see what is working. Let's start with this first. In theory, the MS2130 can do 4K 18 FPS input, which translates to 298 megabytes a second, which is less than what USB 3 can do, but yeah, already quite high up there. And the real limitation are what pixel clock or timing can you really achieve with those small FPGAs. And for example, the cheapest one or the smallest one, you can do like 119 megabytes. And the Tang Nano 9K, which has more input pins and so on, unfortunately can only do like around 100 megabytes a second. And this is because it's a worse speed grade than this one. Yeah. So the one I played around with most is the Tang Nano 20K. It's around $30 US. And you can do 184 megabytes a second with this. And yeah, if you have a bigger FPGA, of course, with a better speed grade, you might be able to do 4K and get this rate. Also quite popular and cheap are those Zinc 710 boards from old Bitcoin miners. You can get for $16 to $20. And yeah, you also can do like 150 megabytes a second there. You need to add your HDMI plug somehow, but there are small adapter boards you can also buy. So yeah, the first thing I did was for this VHS decode project I wanted to try. You can get those 12-bit A to D converter boards also on AliExpress and so on, $25, something like that, and simply hook that up to the FPGA board, which is underneath. And then what is also quite nice, you can buy those HDMI to HDMI 180-degree connector PCBs, which are initially thought to be used for Raspberry Pi 3 when you want to attach a TFT and directly on top of the Raspberry Pi. So you can buy those adapters for like 70 cents, and this you don't need to mess around with another cable. Just put this thing on there, and there you go. So then I think Eric asked, are you going to build an SDR? And I thought, yeah, why not? I always wanted to play with those DVB-S2 tuner ICs. And I already had some at home. And what is nice, they have a lot of bandwidth, like 80 megahertz bandwidth for DVB-S2 and S2X carriers. They, I think, 40 megahertz wide or something like that. And yeah, first test was simply use an ADC, hook that up, and do a test with that. The first I tried was the RDA5815S, and this has a frequency range of 250 to 2,300 megahertz. And yeah, the second test I did with the Rafael Micro RT720, which has a range of 180 to 2,450, which is quite nice because we can also look at Wi-Fi signals and so on. So this was the prototype. I simply retrofitted the tuner IC on the on an LSDR to first try it there, then hooked up an ATD converter to the FPGA board, and yeah, so that actually worked quite nicely. So I thought, okay, probably should do a proper PCB, and yeah, this simply plugs on the Tang Nano 20K. You have the 10-bit 105 megasamples ATD converter here with parallel output. So yeah, you need 20 wires alone for the output. Here's the tuner IC, and this is a 0 IF tuner. So you have I and Q input into the, this is a dual ADC, and yeah, this is the whole thing basically assembled. You can get it quite compact with this 90-degree adapter, and yeah, plugs nicely together. Right now I'm using, you have to connect both the USB 3 for the HDMI grabber and the USB 2 for the FPGA board to be able to control it. But I have a working prototype of this abusing the display data channel for actually controlling it. But right now it needs power via USB anyway, the FPGA board, so I also can use that link. Yeah, so let's do a small demo with 8-bit samples. As we've seen, you can do like 184 megabyte a second. So with 8-bit samples, you can do 90 megahertz bandwidth. With 10-bit samples, you need to do some packing, of course. You can do 72 megahertz bandwidth. So let's fire up Phosphor. Yeah, just resize this a bit. Yeah, so those are 3 5G signals quite close here from the cell tower. What I wanted to show, yeah, this is 8-bit at 90 megahertz, and I can also switch to 10-bit mode. Now it's 72 megahertz with 10-bit. You see the bandwidth just decreased. Okay, yeah, this is a 2.4 gigahertz Wi-Fi here. The ISM band quite crowded, of course. And then there's also some 4G signals here. Yeah, and this is GSM. Of course, this is just a rough prototype, and as you can see here, there's some noise here. Of course, the antenna input is right next to the HDMI high-speed link and so on. So you probably can do a much better RF design, but this is basically just a demonstrator for what this could be used for, and probably quite a few other use cases for that. So yeah. Currently, I'm using the proprietary toolchain, FPGA toolchain from Gowin Semiconductor. I wanted to try the open source IOSIS-based flow, but as I've mentioned in the block diagram, you have the clock for HDMI, and it's then divided by 5 for the pixel clock. And as there is no more free PLL, the chip only has 2 PLLs. I need a clock divider, and this clock divider IP core basically, or primitive, it's a hardware clock divider, is missing from the open source toolchain. And I was in discussion with someone who is currently implementing this, but I haven't heard from him in the last 2 months. So let's see, probably it will also work in the future with the open source toolchain. Also, for this, the reverse direction might just work with using the Osmo FL2K adapters with HDMI out. So if you want to stream data into an FPGA, probably could use that as well. But yeah, then again, you probably just want to use one of those interface ICs. And yeah, of course, you can use this as a logic analyzer, just output instead of the ADC sample some other input. Yeah, so that's it. If you can find more here. Special thanks to Samir Puri, who implemented the HDMI IP core which is basically, there are 2 open source IP cores out there which implement real HDMI. And yeah, this one is written in System Verilog. And that's what I used. Also, Berthold Vandenberg for MS Tools. This is also a reverse engineering effort for the MS. I think he started with the 2109 and 2130. And yeah, this is basically on improving. His goal is to improve the video capture experience and do some reverse engineering there. And it's quite nice. You can hook functions inside the, just like we've heard with BPF trace and so on, you can actually hook functions in the 8051 in there and do some stuff there. And this was of course nice for just peek and poke in the registers. And but in the end, I didn't need to touch the firmware. I'm just overwriting what the firmware does. Yeah, that's it. Any questions?
Yeah, thanks. Maybe I was too tired, but did you define what the hsdaoh actually means, or what the acronym is?
Yeah, in lack of a better acronym.
The title. Okay. Okay.
I googled it, it wasn't used. Maybe it's hard to spell, I don't know.
hsdaoh, yeah. Okay.
Thanks for the presentation. And have you tried to demodulate the digital signals like GSM system information or paging messages through your device?
In the device?
Not in the device, but after receiving the signal through your device.
Yeah, you can. It works as a regular SDR basically. I listen to DAB radio with it, and I haven't looked at GSM, but given that you have this high bandwidth, what I really want to try is do a 4G, 5G cell scanner with this Open 5GS and so on. Try to get a list of cells.
How hardware defined is the frame timing? Basically, with the firmware reverse engineering project, could you maybe modify the firmware in a way that removes all the blanking intervals and stuff?
I think the blanking interval is now pretty at the limit what you actually require to transmit those info frames. The question would rather be, can you get rid of transmitting this extended info frame for telling the device that it's CY?
Yes, entirely.
This alone is one step apparently in what you need to do. So this register is 04 for RGB and 06 for CY CBR, but it's apparently not everything. There's some other thing with the state earlier in the signal chain. If you can get rid of this, you might be able to use DVI input, and then you maybe can reduce H-sync and V-sync even more. But for now, I just gave up with this, and I mean it's even on the Tang Nano 4K, where you have only 10K of block RAM, it works because I need 8K. So quite close, but can do it with the smallest FPGA. Okay.
Yeah, thanks again.
Then, thank you.